Today, we will talk about the conversion between analog and digital signals. If you remember, we talked about the different types of signal. And we said that generally the signals are analog or digital. So because our purpose during this course is talking about the digital systems, we saw that we need to convert the analog signals to digital and then give this digital signal to our system. The microphone, which is a sensor, produces an analog signal. So if we want to send this signal or waveform to the computer to save it, to reduce its noise and other actually tasks that we can do on signal, we need to convert it to the digital form. We cannot send the analog signal to the digital system like computer or smartphones. During this chapter, we want to learn that how can we convert the analog signal to digital signal and then convert the digital signal to analog signal. First of all, we start with converting analog to digital, because here, as you see, we have sensor, and the output of sensor is typically analog signal. So we need to convert to digital. Now first of all, let's define the ADC. What is the ADC? ADC is analog to digital conversion. What is the task of this block? The ADC samples the waveforms. This is the waveform or signal, to produce the sequence of samples. These are sequence of samples of this signal, and transformed by a quantizer to produce binary data. This is the task of ADC. Samples the waveform like that, then using quantizer produce binary data. Now this signal is digital signal. In the input of ADC, I have analog signal. At the output, I have digital signal. As you see here, I have different amplitude at analog signal and also in the sampled signal, but in the digital signal, I have only 0 and 1, which is binary data. Now let's look at how can we do these things. How can I sample the analog signal? Okay, now in the sampling process, the first process is sampling process. This blue continuous signal is analog signal, this curve. Now This analog signal is converted into a sequence of numbers by recording the values of the analog signal at the set of time sampling. Ts is a sampling period. At this period, we sample from analog signal. This is also Ts, this is also Ts, 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 Ts up to the end. Look at here. Suppose that I have a signal, an analog signal like that. For example, now, first of all, I have to determine my Ts, period of sampling period. Suppose that I determine my sampling period will be I don't know, 1 millisecond. This is my T. Now I select determine periods because Ts is 1. This is 1, 2, 3, 4, 5, 6, up to the end. Now, at 1 Ts, I take this value. At the 2 Ts, this value. Third Ts, this value. This value, this one, this one. This is the sampling. This process is sampling. After sampling, now I don't have this signal. I have this sampled signal. Now, with changing the value of Ts, I can have different type of sampling. For example, I can change my sampling, for example, like that. Now, this is the sample signal. This is also the sample signal. But what is the difference between these two sampling forms? The difference is in the converting to digital to analog. Look at here. If my Ts is like that, Ts, and when I want to convert this signal to analog, look at here. This signal can also be my analog signal. This signal can also be. Now these two signals, this sampling form can, the red one, can be the sample of this signal, which is called X1T, and also this signal, X2T. Now, after sampling and converting digital to analog, how can I find that this sampling signal is this X1 signals or X2 signals? How can I determine? This is one of the problems of sampling form. I talked about this problem. I said that if you take Ts like that, after converting analog to digital, now when we want to convert digital to analog, this X1 can be analog signal of this sampled waveform, and also this dashed signal can be the analog form of sample signal. For solving this problem, first of all, we need to define sampling rate. The sampling rate is, you know, that is the frequency. The sampling rate is the frequency. And we know that the frequency is equal to 1 divided by Ts. The sampling rate is reciprocal of sampling period. The sampling rate is reciprocal of sampling period. Now, look at here. First of all, we suppose that Ts, we take the Ts like that. We sample. When we want to reconstruct the waveform will be like that. If we take the Ts like that at this value, the samples will be like that. When we convert it, we will have this signal. But if we select the Ts too large, look at here what happened. Our signal will be like that. Now here we will lose information because we know that the original signal is this. But at the end I have this signal. It means that this signal is not this signal. Now, if you look at here, if I take Ts too large, I will have lose information. And if I take Ts too small, I will waste the digital memory. I will save more information than I need. So this is too important that I select the correct Ts. With defining the sampling rate, we said that we need to have a criterion. What is this criterion? This criterion is Nyquist sampling criterion. The Nyquist solved this problem. What is the problem? What is the question? The question is that, is there a minimum value for sampling rate? We define the sampling rate, the frequency, that still retains all of the information in the original analog signal. The Nyquist criterion says that we can select the minimum value for Fs, that if we take this value, you will not lose information, and also you will not waste the memory. If F max is the maximum frequency component present in the analog waveform, the maximum frequency of analog signal, the sampling rate must be greater than twice the maximum frequency. We said that everything is okay if we obey from this Nyquist sampling criterion. But what happened if I take my sampling rate less than 2F max? It means that the Nyquist criterion is not obeyed. What happened if I select my sampling rate like that? We are saying that if I select the sampling rate is smaller than twice of maximum frequency, a new frequency will perceived, which is called alias frequency. Alias frequency. And this is called aliasing. What is the aliasing? Aliasing occurred when we select the sampling frequency not according to the Nyquist criterion. Difference between Fs and the frequency of analog signal, difference between these two. Suppose that for the waveform cosine 2pf0t, as you see here at this signal, which is an analog signal, the frequency is f0, and we have one frequency. So it means that the fmax is f0. The maximum frequency is the frequency of signal. Now, if I select fs less than 2f0, I will have fa, which is the alias frequency, and the value of this fa is absolute value of fs minus f0. Look at here. Suppose that this signal is sinus 2pf0t, and we suppose that f0 is 2 Hertz. So sinus 4 pi t is my analog signal. Now I draw this signal with between t 0 and 4 seconds. 0 and 4 seconds. Now, using different sampling rate fs, I could select the samples of signal. For example, at this figure, fs is 16 Hertz. What is the Nyquist sampling criterion here? If I calculate, I said that fs have to be greater than 2f max, and our xt is sinus 4 pt. If I'm yes, 4 pt. So it means that f0 is 2 Hertz, which is equal to f max. Now, if my fs be greater than 2 times 2, it means that 4 Hertz, I will not have aliasing. But if I select fs is smaller than 4 Hertz, I will have aliasing. If I select fs greater than 4 Hertz, I will not have aliasing. Now look at here, at this example, my fs is 16 Hertz. Is 16 Hertz greater than 4 Hertz? Yes. It means that I will not have aliasing, and this sampling rate is correct. If fs is 8 Hertz, also everything is okay, because I will not have aliasing. If Fs is 5 Hertz, again everything is okay. But the problem only is that I cannot visualize my original analog signal when I want to convert digital to analog. If I select Fs 8 Hz or 16 Hz, I can visualize my original analog signal. But here I cannot visualize, but I don't have loss of information. Why? Because I obey the Nyquist criterion. The Nyquist criterion says that if you obey me, I promise that you will not have loss of information. Maybe you can not visualize your original analog signal, but you will not have loss of information. Now look at here. If I select Fs 2.5 Hertz, what happened here? Here, this Hertz, this frequency is less than 4 Hertz, is less than twice of maximum frequency of analog signal. It means that I will have alias frequency. What is the value of alias frequency? 2.5 minus 2 will be 0.5 Hertz. 0.5 Hertz, I will have alias frequency. Now look at here. If I sampled my analog signal with this frequency, what happened? I did not take a sample from this section, and also this section, and also this section, this part, this part, this part. I don't have any sample from this part of my analog signal. What happened in this case? It means that if I have alias frequency, I will have loss of information because I don't have take any sample from this section of my signal and also this section of my signal, this part of my signal. Now, that was the principal information about the Nyquist sampling criterion, sampling and sampling rate and sampling period. Now, to convert analog to digital, this process contains two steps. The first step is sample and hold. Here, we maintain the sample value at a constant level. And the second step is quantization. In the quantization, we represent the sampled analog that we can that we obtain from this step. We represent the sampled analog value with a finite number of bits. Let's talk about the sample and hold operation. Look at here, sample and hold operation. Suppose that this is my input voltage with change linearly according to the time. At this time, I want to sample and hold this value. Sample and hold this value. Suppose that I have a capacitor and a switch, and I connect this capacitor to the voltage source. What is the voltage source? This one. Change from 0, for example, up to the, I don't know, 12 volts. Now, if this switch is closed, the voltage of this capacitor, which is called VA, is equal to Vin. Yani buradan gelen gerginlik, çünkü bu switch bağlıdır, gelir düşür hemen bu kapasitorun üzerine. So VA is equal to Vin. Now, when I open this switch, what happened? I don't have this Vin because this switch is off. I open this switch. What happened? The voltage of capacitor remain at this value. Up to when? Up to this voltage, voltage of capacitor discharge. Using a capacitor here, I can hold the value of signal. This is the meaning of sample and hold. Now, this is the time of quantization. How can I quantize my signal? Suppose that I have this signal and I sampled my signal using this duration. The first sample, the second sample, the third sample, fourth sample, this one, this one, this one, this one, and this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I define the bit number. For example, I said that I want to use 3 bits for sampling my signal, and my voltage is Vmax. This is the maximum value of my voltage. How many number can I have with the 3 bits? 2 to the power of 3, 8. I divide my interval 0 up to Vmax to the 2 power of B minus 1. This is my delta, which is step size. Divide this section, Vmax divided by 7. Here is Vmax 7, 2 Vmax 7, 3 Vmax 7, 4 V7, 5 V7, 6 V7, and 7 V7, which is Vmax. This is step size. This duration is step size, delta. This is TS, sampling period. I divide to the 7th section. Now I write this is the 0 volt. I divide this duration 0 up to Vmax. This is my 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Am I right? From 0 up to actually 7. Now look at here. Now each sample belong to a specific code. For example, the sample 1 belong to this code. This is sample 1. The second sample belong to this code. Sample 3 belongs to this one. This sample belongs again to this one. This sample belongs to this one up to the end. For each sample, I define a binary code according to this division. This division is delta, my step size. I said that, for example, this value is near to this line. What is the code of this line? 1, 0, 0. Now what happened? Suppose that I have this sampling rate, this sampling data, and I determine that this code, for example, is belong to 101, 001, 000, 111, 101. What happened? For each sample, I will have this code. Analog to digital converter. 0, 1, 0. 1, 1, 0. 0, 1, 0. Up to the end. Now what is this digital signal? Is like that. Now goes here. At 1 I have low level, at 0 at 1 I have high level, at 0 I have low level. Now this is a digital signal.